Now we're going to talk about multiplication of two matrices. Remember, we have defined matrices, a matrix as a two-dimensional array of numbers where m sub ij is the ith row, jth column element of that matrix. Now, what is the condition to be able to multiply two matrices? The number of columns in the first matrix in the multiplication must be equal to the number of rows in the second matrix. So that's what we're looking for. The number of columns in the first matrix must be equal to the number of rows in the second matrix. For example, if this matrix M has 2 rows and 3 columns, we can say this is M sub 2 cross 3, 2 rows and 3 columns. So that's basically first row, first column, second column, third column. We can say that the row number is 2 and the column number C is 3. Then if we have another matrix N, which consists of 3 rows but 1 column, so N is another matrix with 3 rows and 1 column. That is to say, here we have R is equal to 3 and C is equal to 1. Now here you can see that the number of columns in the first matrix matches the number of rows in the second matrix. So these two matrices, M 2 by 3 and N 3 by 1, can be multiplied. So if we perform this multiplication, we multiply matrix M with matrix N, we will obtain a matrix P, which is going to have the number of rows in the first matrix and the number of columns in the second matrix. So this is going to be a 2 by 1 matrix. Okay, so how do we find the elements of the P matrix? So the first row, first column will be multiplied with the first row, first column in the second matrix. It will be M11, N11. The first row, second column will be multiplied with second row, first column, M12, N21. And M13, first row, third column in the first matrix will be multiplied with third row, first column, N31, giving us the first element in matrix P. So the first element in matrix P is M11, N11 plus M12, N21 plus M13, N31. And for the second element, this is going to have 2 rows, 1 column, remember. We have M21, N11, M22, N21, and M23, N31 multiplied and added together. So the second element of the P matrix is M21, N11 plus M22, N21 plus M23, N31. So you can see that these two numbers are the same here. So this is giving us P11, and these two numbers are 2, 1, 2, 1, and 2, 1, and this. So this is going to give us P21. So that's the second row, first column of the P matrix. And this can be expressed in terms of the matrix element as the ith row, jth column element of the M matrix is multiplied with the jth row, kth column element. Now, if we have a repetition of the two indices here, Einstein's summation notation tells us that this implies addition. So this is going to be added over this index, and it will give us the ith row, kth column of the P matrix. So this will give us PIK. All right. For example, when I is equal to 1, we have M11 N11 gives us P1 1, M11 N11 plus, because this is addition, we're going to have M12 and 21, and then we will have M13 and 31. So this J matrix can take three different values. J index can take three different values. So that gives us P11. And for I is equal to 2 here, it's M21 N11 and M22 and 21 and M23 and 31 will give us P21. So that's basically the way it works. And this is written this way using the subscript notation. And the repeated J index implies that there is an implied summation over the index J here. Okay, so for example, P11 is M11 N11. So these ones are going to be the same, but the J index will be changing. So it's going to be M12 N21 plus M13 and 31, because the summation is over the jth index. All right, so that's how we perform matrix multiplication. And what about the matrix representation of a vector? So we have seen that we can write this vector A in terms of its components as A1 E1 hat plus A2 E2 hat plus A3 E3 hat, and E1, E2, E3 were our basis vectors. And this vector A also has a matrix representation. We can show it as matrix A. It's going to have 3 rows and 1 column, A1, A2, A3. So we're going to write all the components of vector A in a single column. So you can see that this is one way of specifying the matrix. The basis vectors are not specified this way. Or we can show the same matrix using the transpose of this matrix. So vector A can be represented as a single column where all rows have different values, the components of vector A. So A1, A2, A3. This also represents the vector A. This is basically obtained by transposing this one. So first row, first column stays the same. Second row, first column becomes first row, second column. Third row, first column becomes first row, third column. So the rows and columns exchange places. And this is called the transpose operation, transposition. Transpose of matrix A is the interchange of the rows and columns. So that's how we obtain the transpose of a matrix. And we can note here that this vector A can have an infinite number of matrix representations. depending on the choice of basis vectors. It depends on the choice of basis vectors. So if these are ex hat, ey hat, ez hat, these would be I hat, j hat, k hat, the Cartesian basis vectors, for example. But we can have a different choice of basis vectors, and then these numbers will obviously change. So we can have an infinite number of different matrix representations depending on the choice of basis vectors. Now, if we do some operations on these vectors, for example, if I take this vector A, which makes an angle theta with respect to axis 1, it has a component A1 on this axis and A2 on axis 2. And then if I rotate this vector by an angle phi in the counterclockwise direction, so that the new angle it makes with the one axis is theta plus phi, I would have a different component, A1 prime and A2 prime. The projections of this vector A prime, the new vector that's obtained by rotating the old vector A by an angle phi in the counterclockwise direction. This is one operation I can perform on this vector. So this vector A prime is generated by rotating vector A through an angle phi in the counterclockwise direction. Okay, so if I perform this operation on this vector, I can clearly see what will happen to its components. So let's worry about that. This vector A has two components originally, A1, E1 hat plus A2, E2 hat using the axes 1 and 2. Its magnitude is the absolute value of vector A, that is A1 square plus A2 square root. This is obtained by using the Pythagorean theorem here. You can see this is a right triangle. This is A1, this is A2. So A1 square plus A2 square is equal to A square. So that's how we find its magnitude. And A1 is the projection onto the first axis, which is the magnitude A multiplied by cosine theta. And A2 is the magnitude A multiplied by sine theta. So that's how I find the projections. Now, when I rotate this vector in the counterclockwise direction by an angle phi, the angle with respect to the first axis becomes theta plus phi. So I'm going to have a new vector A prime, which will have A1 prime E1 hat plus A2 prime E2 hat. And that is simply the magnitude of the vector doesn't change, A. Cosine, the angle has changed. It's theta plus phi E1 hat plus the projection onto the second axis, A times sine theta plus phi E2 hat. Okay, now you can see what happened to these components. A1 prime is A cosine theta plus phi, and A2 prime is A sine theta plus phi. And using the sum of two angles cosine formula, I can write this as A cosine theta cosine phi minus A sine theta sine phi, which is A cosine theta is what A1 was originally. So it's A1 cosine phi, and then I have minus A2 is A sine theta sine phi. And for the projection onto the second axis, I have sine theta plus phi, so that is A cosine theta sine phi plus A sine theta cosine phi. So that's sine theta plus phi, sine theta cosine phi plus cosine theta sine phi. And A cosine theta is already A1. So this is A1 sine phi. This will give me A1 sine phi. And A sine theta is A2. So this is plus A2 cosine phi. Now, using the matrix representation, I can write the components A1 prime and A2 prime in terms of A1 and A2. So matrix A has this matrix representation A1, A2, and matrix A prime has this matrix representation A1 prime, A2 prime. A1 prime is A1 times cosine phi minus A2 times sine phi. So here I need to have cosine phi as the first element and minus sine phi as the second element. And for A2 prime here, I have A1 sine phi plus A2 cosine phi. So here I need sine phi and cosine phi. So the multiplication of these two matrices, this is a 2 by 2 matrix, this is a 2 by 1 matrix, it will give me a 2 by 1 matrix, which is this one. It is cosine phi A1 minus sine phi A2 is A1 prime, sine phi A1 plus cosine phi A2 is A2 prime. This is my rotation matrix R as a function of phi, so that the matrix representation A prime can be obtained by multiplying with the R matrix, the rotation matrix, with vector A. So this gives us the rotation operation on this vector. And if I write this as a row, that means I have to take the transposition of these two sides. A1 prime, A2 prime, interchange of rows and columns here. A1, A2 multiplied by this matrix transposition. So when I take the transpose of a vector A prime of this matrix, it is A transpose multiplied by the rotation matrix transpose. So that changes the order of the two in the multiplication. So that means I have A1 prime is equal to A1 times cosine phi, so that's the first term here, cosine phi, and A2 times minus sine phi, so A1 times cosine phi, and then I have A2 times minus sine phi, so this is minus sine phi, the first element, A1 times sine phi plus A2 times cosine phi is A2 prime. So A1 cosine phi, A2 minus sine phi, and then I have A1 sine phi, A2 cosine phi. So remember, A1 cosine phi minus sine phi A2 is A1 prime, A1 sine phi, A2 cosine phi is A2 prime. So when I take the transpose of this equation, I have the matrix A transpose multiplied with the rotation operation matrix transpose. Okay, so if I use the subscript summation notation, so using the subscript summation notation, the Einstein summation, the vector components AI prime are found by multiplying with the R rotation matrix Rij Aj, or this can be written as Aj Rij since I have the repeated index j here, this implies a sum over the index j. And the A prime matrix actually has components AI prime written in terms of the basis vectors EI hat, and this is just Rij Aj, which gives me the components of vector A prime multiplied with EI hat. So you can see that I have to sum over the j values here in order to obtain the ith component of the A prime, and then I have to sum over the I values here to write the total matrix. So this is how I represent this result using the subscript summation rotation. Okay, so here we've talked about matrix multiplication. If we write a matrix, a two-dimensional array of numbers where Mij is the ith row, jth column, in order to be able to multiply two matrices, the number of columns in the first matrix must be equal to the number of rows in the second matrix, and the number of rows in the first matrix and number of columns in the second matrix are the values for number of rows and columns in the multiplication, in the product. So that's how we do it, and we can write this multiplication process using the subscript summation notation as Mij njk is equal to Pik, where the repeated index implies summation over that index, as we can see here. And we can also represent a vector either as a single column or a single row. If we represent it as a single column, it would be like this with three components, and the basis vectors are not specified here, so these numbers will change depending on the choice of basis vectors, so we can in principle have an infinite number of matrix representations. If we take the transposition of this, we obtain a single row representation of the matrix, and the transposition is the interchange of rows and columns. Now we started discussing vector operations. We started out with rotation. If I take a vector A, and which makes an angle theta with respect to the first axis, and rotate it by an angle phi in the counterclockwise direction so that it makes an angle theta plus phi with respect to the first axis, its magnitude doesn't change, but its components, its projections onto these two axes change, such that we have a prime vector will be equal to a cosine theta plus phi times e1 hat instead of a cosine theta e1 hat, plus a sine theta plus phi e2 hat instead of a sine theta e2 hat. And using the sum of these two angles in cosines and sines identities, so trigonometric identities here, I find the basically using the matrix representation, I can write this as the vector A prime is a rotation matrix multiplied by vector A, where the components can be seen by using these trigonometric identities. And if I write this as a transposition, then this is going to be a single row. This is going to become a single row as well, but it will change places with the rotation matrix, and rotation matrix will get transposed as well. And here I have explicitly proven that. And these two results can be also written using the subscript summation notation. And we have seen that the vector components for the primed vector is Rij Aj, so it's basically representing the matrix multiplication here. And the A prime vector can be written in terms of its new components, Ai prime in the Ei hat basis vectors here. So the I index, repeated index, implies we have summation. So this is A1 prime E1 hat, A2 prime E2 hat, A3 prime E2 hat, all added together. And where the Ai prime is Rij Aj, so that also implies summation over this index j. So we have R11 A1, R12 A2, R13 A3, etc. So this is basically since it's a 2 by 2 matrix, it's R11A1 and R12A2. So we don't have the third one. Okay, so that summarizes what we have discussed in this video.